I'm going to start the presentation with an agenda that will include a brief introduction in the content of this webinar. I would like to show you a sample workflow on how we're going to show the basics of petrophysics, focus towards that rock physics approach. I'll talk a little bit on data prep and QC. Then I'll move towards the petrophysical evaluation itself and how we use it in rock physics, and I'll close the webinar with a summary. So I would like to start the webinar with two core questions that are going to be touched throughout the webinar. My first question is about the petrophysical inputs themselves and what are they and how we use them for, how we could see them for rock physics purposes. Also, how is this interpretation used for a consistent rock property analysis and modeling? And before we get into the actual content, I like to remind people about the two disciplines themselves, because more often I hear some people, like me, I wear both hats, and some people don't know the difference, or they do know the difference, or if they do, they keep it isolated. I think there is a lot of overlap between the two, and we need to keep it, as close as possible because they depend from each other. So in petrophysics, we talk about logs for formation evaluation. It's similar to rock physics, but it's a little bit, seems to be less focused on sonic data. For rock physics, we study the relationship between geophysical measurements and rock properties. And we put a lot of emphasis on seismic, sonic data, and the ultrasonic data. So why does it matter? In this display that I have, I try to capture, let's say, an example of an integrated approach that we do at ICON. So the key message that I want you to take from here, for those colleagues that are listening to me right now and they're staying on the petrophysical bucket, if you want to put it like that, is that we are at the very beginning of the chain. Data QC is super important. We have a lot of data. The number of versions of data, it's massive. It could be overwhelming at times. So the data management itself play a huge role for us. We control in terms of that QC, all regarding reservoir and non-reservoir properties. Once the QC is done and the wells are conditioned, we eventually move toward the next phase, which is the rock physics modeling. This is an example on an unconventional, by the way. And if we split the workflow into two, let's think about G&G. Are those inputs going to be used for rock elastic and mechanical properties? What about trends? Are we providing the right input to them? As geophysicists will think of well ties, the person is going to process or condition the seismic and eventually tie the wells that will fit into an inversion for ultimately generate acoustic impedance values, for example, BBBS, Young's modulus, you call it, in order to characterize the reservoir and ultimately characterize or determine where the phases are. So this is key, that when we work on data, we know who are we feeding and vice versa. So before I start, I like to always put things into a phase. I'm very process oriented. So I broken down as an example of petrophysics for rock physics. And I've broken it down into 4 phases. You'll have on the top a funnel with inputs, and at the bottom, we'll have some examples of data outputs. So the first, as I mentioned before, is the data QC. In here, we look at all the data, log, core, whatever data we have, sometimes lots, sometimes little. We focus on log correlation, core to log quality, data selection, etc. In the petrophysics bucket, we actually get our hands dirty and we work on the core to log calibration, mineral analysis, we generate porosity and saturation, and eventually we generate and provide or help with those litho-facies calculations. I have the next bucket, which is the rock physics itself, and this will be more towards the seismic petrophysics when we combine the two. We generate reservoir versus non-reservoir models, data reconstruction. Perhaps in phase 1 or actually the petrophysical phase, we have already done some corrections, but can we use a model instead? What are the velocity porosity relationships and how that data from before is being used into that calibration? We probably refine more the litho-facies in terms of elastic space. And as an example, those models and that raw physics model that we generate could be going into a 1D modeling, could be going into an inversion. For this example, I have a 1D modeling, let's say upscaling, we can do a well tie, we can do synthetics, aviomolding. So all these phases are tied to each other. But again, I would like to press, and you will hear me a lot saying this, everything depends on the knowledge that we have of the rocks, which is mainly attached to the petrophysics workflow itself. So let's start with the first bucket. And what data do we need? Lots. We are very famous. People always tell us you ask for too much or you care for too many details, but rocks are complex and we have to understand the details in order to calibrate the model properly. So here's a list. It's not an ultimate list, but in terms of order of priority for rock physics purposes, which is the theme and the topic of the webinar, the very top line represents our main elastic sweep log. So for us as petrophysicists, we need to understand that the density, the P wave and the S wave are properly conditioned in order for us to be using that in rock physics models. So as you can see, we have a lot of data, neutron, caliper. Many of you will say, yes, this is pretty intuitive, but all the integration of this data is what will ensure that we have a successful calibration and understanding of the reservoir itself. At Icon Science, we use different platforms, like for example, in data management, which is a huge time-consuming task, we use iPoint, and it's tied to our petrophysical interpretation as well. So you can mix the two eventually to put them into the rock physics workflow that Icon will use RockoDoc, of course, and it will all be synced together. But everything has to be in line. I really push on this because data seems to be everywhere. And also as petrophysicists, we need to ensure that the right set of log is provided to our GNG or geoscientists themselves. No one better than us knows what they are and how they should be used, and what caution we should pay attention to. So let's look at some issues that we see commonly, and these are pretty traditional ones. These are like book examples, but I think they are important. Sometimes we tend to overlook at them, and they could cause us troubles later on in the workflow. So on the left, we have a case of a depth shifting. On the right, we have an example for a casing point. The dotted line on the left example show you the misalignment that we see between the two versions, the before and after. This is a density and neutron log. And you can see, some people say, how much do we worry about? Well, it depends, what is the resolution of your logs? What kind of scaling are we looking at? In this particular case, I would say it's significant. Let's say the density is not too much of a concern if we compare it with the velocity that we don't have here, but actually we do. And but let's say the neutron and the density are going to be used for the petrophysical model. These 2 points will be erroneous in any calibration, so we need to take care of that. Same thing for casings. If this is a type of data that is going to go into a well type, for example, this artifact will cause significant problems. I know that this could be obvious, but sometimes even issues like splicing different runs that we think are obvious to us may not be intuitive to other people. So we need to make sure this editing is done. Some of the correction practices that we can think about, besides the bolt shift in this case, it will be a stretch and squeeze. Sometimes just a single bolt shift is not enough, and we need to take care of that. In reality, it's more common to use stretch and squeeze, more common than we think. I like to tie the simple and the easiest first, the most obvious members, simply because those are the ones that are going to be tying my interpretation. And then I worry about the stretch and squeeze. Now, how are we going to correct the data? Do we go multilinear approach? Do we use analog data? Is there a matter, do we have a problem with time, machine learning corrections? Is it possible? Despiking. Can we use a model instead? So these are some techniques that we can apply prior going into an interpretation. So think of data quality in rock physics all the time. Here's an example where we have a bad hole indicator on the left, and you can see that the red curve that it's highlighted here that I'm pointing at has been it doesn't show where the actual borehole goes damaged. This is very obvious that we have a rugosity problem, and just because of the nature of the measurement. And my message here is that even though some people will tend to remove the point, some people will tend to correct it, be aware that this is already uncertainty whether we are introducing into the impedance calculation that is going to be used for rock physics purposes. So additional well control or analog data can be used for data reconstruction. But I'm highlighting this in red because we need to be careful what we assume. Just be honest to yourself, be aware of the uncertainty, and sometimes you have enough well control that you can trust the approximation, but some other times maybe we need to go with analog data from a different place just because we don't have well control. So be aware of risk, because when we look at these inputs going into spaces like BP and density, this is a multi-well example color-coded by V-shell. We need to be aware that we understand what we see. And I'm superimposing here constant impedance lines. So in terms of raw physics, we need to be aware that artifacts are now being introduced to the trends that I'm seeing. Velocity. Now, velocity, it's the least used sometimes by the petrophysicists. I personally like to explore a lot with the slowness in my petrophysical models where applicable. Of course, I'm tied to core in these cases. So when you QC the logs, here's a QC that we can apply using the semblance data. These are very powerful tools. As you can see here in the monopole semblance, we can see that the actual final output from the provider is an average between the two. So sometimes you could say, okay, we can use that trends, we can look at things, and it'll be obvious. But most likely, you know, there could be iffy areas or gray areas where we don't really see. I think it's a very nice visual way to see where it's good versus not between the two signals. And for the shear wave data, it's the exact same thing. So even though the shear is less used for petrophysical purpose, I do really encourage the community to kind of merge the two because when we use attributes such as Poisson ratio and BPVS, we can have another piece of QC that will help us understand lithology, for example. My advice, compare all the available shear log, like in this example here, we have dipole and monopole sonic. Are we dealing with fast versus slow formations? Where is one more suitable than the other? Select the most appropriate response based on what you know, but bear in mind that they have different ranges and different precisions. And reevaluate, these are waveforms that can be imported into software, reevaluate the processing if necessary, because sometimes we could be dealing with dispersion problems. So why do I push a lot on QC? And this is kind of like, I would call it like a quick summary slide, because if we look at all disciplines, I'm going to focus just because of time on petrophysics and rock physics, and we look at different focus, let's say compressional, shear, litho, fluid, contrast, space, and their sources. You know, in petrophysics, let's say, let me pick, for example, shear. Even though we'll be thinking about lithologies in petrophysics, but my rock physicist community will be thinking about, you know, the moduli of mu over rho that will determine that shear data. So what about lithofluid? How we use a lot of neutron density, even photoelectrical factor, but it's my density itself, the one that we're gonna be looking in rock physics. So this is the core of everything we do moving forward. And I really, really think we need to pay more attention in how we over and underestimate sometimes these inputs just because of time. I've been there, done that, but it is quite crucial that we do it correctly. So moving into the next portion of the workflow, which is the petrophysics, and I call this like a validation stage, because when we do petrophysics, sometimes there are multiple situations, but a lot of times, you know, the petrophysicist finishes the job and pass it, things don't happen until a certain time, and then when the rock physicist come into the game, oh, we found problems, your fault, my fault. So ideally, we want these two to be talking to each other a bit more. It's more of a synergy type of scenario in the ideal situation, because everything we do in rock physics will be fed from the petrophysical model. So let's start with some lithology and mineralogy topics or points. Here's a Gulf of Mexico example, and I took this from Vernick. And on the left, you have a channel cut sand, and you can see the associated litho-facies, or the associated lithology. I have to correct myself on that. We have the mineralogy on the next track, and here you can see the nice space in both upper and lower section of the sand. The right sand, it's a splay sand, But what I'm trying to point in here, and I would like you to also refer to the ternary plot that will control the mineralogy proportions in the two, and referring to the sands. This is just a theoretical example, of course. Is that a lot of times we hear people interchanging the terms shale versus clay. They are not the same. And we need to make sure that when we look at raw physics workflows, the input that we're putting into the petrophysical input that is coming is an actual mineralogy volume. So what is particular in these two, and I would like you to look at that, is that these are these two sands, even though in the splay sand we have a variable content of clay, the shale volume or the shale itself is set to 0. Simply because, you know, this is a very clean sand, but here it's not. So be aware of that. And when we look at raw physics, I repeat it again, please think of mineralogy, because it's going to be used for determining the solid moduli, and therefore, or after that, the well-derived facies if we're using mineralogy to control those. So staying on the same lines regarding shale, for example, here's a classic example, and this is very common. This is a multi-well cross plot of peak wave velocity and density, and it's the same plot that you saw before, but now what I had not said before is that these cross plot contains different types of interpretation of shale content for very similar wells. So in reality, when we work with multi-well data, especially different vintage data, you can have different approaches of calculations. For calculation, let's say neutron density, was the resistivity right, multilinear, or even gamma, you know, multiple gamma. So what cutoffs were applied? So having a consistent approach will ensure, from a rock physics perspective, that we capture the correct trends. Here, for example, the before and after, it's clear that we can see now how nicely the shales are being highlighted after a proper conditioning. So in terms of raw physics, why is this a big deal? It is because the mineralogy calculations that we provide are going or will be expressed in terms of attributes. So in the ideal world, we want to express or identify type lithologies, or the domain of what we're looking at, and how they compare from each other. On the left, I have a cross plot of density velocity again, and in terms of petrophysics, we can think of density slowness, and it will be the traditional plots that we see in our packages. But in raw physics, we think of velocity, peak velocity. So these are expected trends that we see for given different lithologies. And there are going to be some QCs that we want to introduce in order to avoid artifacts. Let's say, do we have the same sandstone? You know, is the limestones always tight? Do we have a chalk instead? What do I expect in my column? And if you look at the same plot but in attributes, those are the type of derivative implications, I would say, that will be captured by whoever is inheriting the petrophysical model. Let's say our geologists. You know, where do they expect a certain lithology to fall? And sometimes we do see artifact, and it's as simply as a bad or a poor editing, or sometimes it's a misunderstanding or incomplete data or knowledge of the rock themselves. Now let's look at porosity. So here's a plot of a traditional porosity calibration log to core, and porosity plays a big role in the rock physics. It's used as the basis for a lot of things, including the calibration of the model. It's also the basis for invasion correction, and in this particular example, you can see between the porosity and the saturation tracks that has been done. So when you have a hydrocarbon facies or hydrocarbon charged reservoir, a correction for that is recommended. And fluid properties also need to be consistent with those that will be used in the modeling themselves, let's say fluid substitution. So various methods could be used for the porosity itself. In rock physics, just bear in mind that the actual porosity that will be used is the total porosity. For multimineral rocks, variable solid density as a function of depth is highly recommended if you're using a density-derived porosity. The ideal scenario, of course, as you see in this example, is a core to law calibration that we often use in our multi-mineral solvers. Now, for rock physics, if you look at this modified plot from ASVET, which is porosity and Shear velocity, it is a huge implication not to have a well-calibrated porosity, because in this domain, rock physicists can interpret different changes in the reservoir stiffness pattern. And we can also interpret things such as cementation and sorting. So imagine just moving one point to the other just as simply because we are not calibrating properly the porosity. It will directly affect the impedance and or the P wave velocity space and their equivalent impedance range. Another correction that can be applied, and we sometimes ignore, is because we have deviated wells, is the sonic correction. So this is an example of deep water, and there has been an isotropic correction applied to the data. On the plots that we have on the right, we can, I would like to highlight this also from Wernick, the relationship between V shale and anisotropy. We can see how nicely the Thomson parameters and isotropic parameters correlate to the petrophysical property. Now, in this assumption, of course, we're saying that the sand itself is quasi-isotropic, and these are corrections that can be done. The before and after is in blue and red for S and P wave. Can be done if you know the deep angle of your beds. In conventional shales, by the way, the anisotropy parameters can vary by clay content, mineralogy, or even the preferred orientation of those clays. Let's complicate things a little bit, because Mother Nature is not that nice sometimes to us in terms of oil and gas. So unconventional rocks are going to include a different challenges. So there are some implications that we need to consider. Here is some images, CAM images from Miller in Haynesville, Marcellus, and Eagleford. The first thing that we know, and this is probably, yes, no-brainer, we know that these are highly heterogeneous rocks that could be mixed with conventional and unconventional reservoirs. Let's say sandstones mixed with Thai carbonates. And on top of that, we mix them with organic shales like the examples in the Permian. So when we look at the petrophysical model, we need to apply also better techniques or techniques that consider the multi-mineral nature of this rock that are nicely represented by this theoretical ternary plot here. We also have variable properties within the same facies, and we have complex porosity systems that could be attributed to the non-kerogen portion and the kerogen portion itself. Anisotropy is another concern. What's the layering? How my clay is oriented? Are there any fractures? The TOC itself. And to complicate even more, because not all wells have core, the petrophysics that we apply in these rocks have to be highly dependent on core calibration. And that's one of the challenges that we commonly see in these, because we will have to extrapolate properties based on the core calibration from one well to the other. So here's a porosity, here's a breakdown in how we can look at porosity in organic rich reservoir. This is a model from Wernick. And the idea here, I'm not gonna go into the details of the model itself. What I'm trying to say is that given the complexity of the reservoir, we're splitting the way we assume the rock for porosity calculations and TOC relations. So the rock here has been split into two portions, the kerogen portion and the non-kerogen portion, that are dependent on the kerogen concentration of the solid rock density. So with these models, we can generate rock physics models that can be used as a calibration point for a kerogen-dependent model for porosity. And when you look at this template, which is a density and TOC for two different wells, what we can observe is that different trends in the data. One could say this is pretty linear, but most often, we could think, sometimes people say, okay, I will run a density line and that will be enough, it matches my area. But the more core we get, the more tweaks we need to apply to a density, let's say a smoker type of relationship, and the predictivity of the model starts failing because we'll have to tweak as much as possible. The beauty of this one, which I personally like is that we will capture variations in the data itself as a function of keratin porosity. Here's the same this is a similar application of a petrophysical input into a rock physics calibration. And this is in the Permian. This is density and P-wave data. On the left, we have data from Bone Spring Formation. On the right, we have the Avalon. And the left plot is color-coded by V clay. And now I'm thinking in terms of mineralogy. And I want to highlight it because I often hear people say, oh, a shell or a clay. No, they're not the same. So, and what the model is going to provide to the rock physics calibration is a good understanding on how these lines should behave in terms of the data itself. This is a line for clay-rich sediment. This is the line for sand, and this is the line for carbonate. So the idea is that we understand what would happen to my facies as a function of a change in mineralogy and porosity, of course. On the right, we have the Avalon, and we can also use the model, which is Bernie Cashano, my mistake not to pronounce the reference. And this is from Del Moro 2020 paper, if you want to look at the details in the Permian calibration. So this is a model that we could also relay, but now in terms of TOC. Again, this is a petrophysical input with velocity space, hopefully both. This has a model already in place, and this has been correctly processed, and we superimposed a rock physics template that is changing as a function the clay content. And you can see that the overall, the trends are quite nicely captured. Now, I know in rock physics, we don't talk a lot about P-wave and S-wave data, but even if we provide a P-wave data and it has to be properly conditioned, you know, remember my QC on the shear loss with the semblance plot. Using BP and VS can also help me understand changes in my rock. Could it be a change due to lithology, fluid, or even pressure? Let's look at this plot on the left by Vernick. It's a P wave and versus VS. And we are looking at different BP-VS relationships for unconventional shales. You know, the one thing that stands out is that the Avalon, which is the one in blue or light blue, is standing out quite a bit, given the dynamic relationship between the two properties or variables for the Avalon. So what's happening in this case is that the Avalon cloud or the Avalon data cluster is changing due to a high quartz and low clay content as well. So when we plot that data and we look at the VPVS for that, and we look at an Avalon example, you know, having a model in place can help you understand such variations, such as, you know, what would you expect from a rock that is non-keratin rich versus the actual organic shale. And these are very powerful tools because in some cases where we don't have S-wave data, what the rock physicists are going to do, they're going to generate a P-wave dependent or a mineralogy dependent model that will predict the S-wave data where they don't have it. So having a proper petrophysical interpretation in place will allow us to successfully calibrate any outcome from this space. And I really think it's quite useful in terms of even when we don't know if our petrophysical model is not correctly predicting what we expect. Try VPVS, try Poisson ratio, you'll be surprised, I would say, in how helpful it could be. So let's look at some multi-well data, P-wave and density. In petrophysics, we like a lot of histograms and we do them all the time. So in rock physics, we do that too. And the idea is that we generate trends. Of course, you don't want to mix things that are not comparable, but when we have multiple data, you want to be careful in how you lump the data. In petrophysics, we question ourselves a lot. How do we lump sections? And petrophysicists do it too. You know, how do we break it down? And the ultimate goal, as it's shown in this example in the Delaware Basin, is can we generate different spaces that are related to lithology? So here are some elastic phases that have been computed in terms of mineral interpretation. And you have phases 1, 2, and 3 in blue, green, and red. And that's one of the goals when we use multiple data and multiple petrophysical analysis that are going to go into regional studies, for example. So shifting a bit, I don't know if you remember, but I mentioned sometimes we have to explore different things. This is something that is ongoing for us at the moment. And I was a little bit skeptical myself when I tried it, but we are given sometimes a lot of data and not enough time. In some cases, approaching these problems with a machine learning prediction, it may not be so crazy. Now, is it going to be completely tied to the core? I don't know. Is it going to be sufficient for fast track analysis? Maybe. Now, here's an example where we use density gamma, neutron, P wave, and deep resistivity. And we had already, this is a supervised approach, by the way, and we had already calibrated a petrophysical model for neighboring wells that we consider, based on some criteria, they consider to be within the same type of wells. Now, what we have found, and this is just an option, I'm presenting options to you and as a way to diversify in how we can provide the same outputs. What we have found is that the mineral predictions were less sensitive. When I say mineral, was the clay, calcite, and quartz, than the actual kerogen and porosity. They were quick and stable, the predictions for a lot of wells, but we needed the caveat here, as any of these techniques, as you may know, is that we needed to have enough well control. Dissonation was important, but guess what? It was, again, controlled merely or entirely by the petrophysical criteria. I mean, rocks are rocks, but they are complex. So we need to make sure that this information that we know from the very beginning of the life of the well is transmitted to the geophysical and rock physics community. Optimization is required moving forward for this particular example. And as again, don't take it as a ground truth. For these case, it's ongoing. Now, those mineral models can be used for more interpretation. So I did mention already some litho-facies. So what it's done in terms of the elastic space for rock physics purposes is that most of this data is gonna go for inversion projects. Let's say an example. In this particular one, we actually, the ultimate goal is run a GIFI inversion. And here you see a cross-section of some Permian wells in San Simon County. So the petrophysical data has been used and merged with elastic responses to define the litho-facies that you see in these tracks. So you have, for example, limestones in dark blue, you have siliciclastics or quartz-rich facies in yellow. There are some facies that actually came up as undefined, not enough information. We still don't understand if these are actually real, or I simply don't know yet what's going on from a petrophysical perspective, or I need more data to feed the model. So there's no single criteria to define these facies, but just keep in mind that is the porosity, is the saturation, is the mineralogy what is driving all these classifications. Now, let me go to the last bucket or the last phase of the workflow that I showed you at the beginning. And let's see some other applications of petrophysics merged with rock physics and how they're put into place. So traditionally, when we look at logs and depth, we look at trends. We run trends all the time for ourselves. Here's the before and after initial and updated model. And the idea here is, what do we expect in terms of ABO? Is it a class 1? Is it a class 2? So what has been done is a first pass of petrophysics was done, and it just wasn't even a mineralogy. It was, let's say this is a lithology volume, by the way. So it was just, we shale and that's it. So what the rock physicists did, that's all they understand of the borehole. They calibrated a model that is represented in magenta. The original logs are in blue, and these are P wave, S wave, and density. They generated the model, and what's happening is as soon as you hit certain interfaces, the model starts mispredicting the in situ data. Models are models. I mean, they're as good as data you give. So what has been done in the update version is that we provided a more in-depth lithology volume that was fed into the model, and they use this synthetic models to see if they can compare to the in situ. Now, when you do that, look how much better, it's not great yet, but look how much better the marley section has been captured, just as simply because of the calcite tweak. Now, this is like the everyday for a lot of geophysicists. This is an example of an isotropic corrected logs. BPBS and BPBS has been corrected for an isotropy. The measured data is in black, and the model data or corrected data is in red. So what you see in the synthetic panel, the middle track, those are actually the seismic, that's the seismic response. On the left, we have, oops, that was me. On the left, we have the raw data, and on the right, we have the corrected data. So when we look at the bottom reservoir, the first thing you can see is that without that correction, we would have never been able to match the reflector and their associated, or its associated ABO signature at the top of the reservoir. Last but not least, I have an example from Del Moro, a very good paper. And here is data from the Permian. And I'm just showing you, it may not look obvious, but this is the outcome of all those RPM calibrations that you saw before multiple times. And I'm drawing like a boundary. I don't really believe in those boundaries, but I'm trying to make it as far apart as possible. But when you look at this log plot, you know, from velocity to the gamma, it's the petrophysical space. All the model calibration came from the TOC model that was provided to them. And what we've done is, or what was done in this case study, is that the calibration has been done in a space or series of spaces. A model has been identified and then has been used to perform what-if scenarios and understand the synthetic response equivalent to that. Now, then you can see is that after a 50% reduction of the TOC in the upper and lower avalon, the isotropic and anisotropic rate traces have been computed. But most importantly, we want to compare, let's say we don't have wells, all the wells are in the same average, or some wells are one average TOC and some others are not. So what the raw physicists want to do is, what if that TOC changes? Or is it the change that we're seeing in the seismic attributed to a TOC change? You can play both ways. So let me wrap up with a quick summary. I have on the right, I like workflows and pictures and all that. So I have a modified workflow from Vernick, and this is mainly to wrap up how you would summarize a seismic petrophysics workflow. So on the top, I've placed the petrophysics, let's say core to log, but it's always at the top, okay? A lot of people can do the workflow without the logs or without any processing. I'm just showing you the best practice and how we recommend it to be done. This petrophysical model fits into reservoir descriptions like that are into the seismic petrophysics world, inversion, etc., and the geological model. Ultimately, because we want to characterize a reservoir and proceed with let's say, reservoir simulation. So in general, an integrated petrophysics approach, raw physics approach type, this is the most optimal practice for what we're trying to do. Fast tracks are okay. I mean, I've done them, you've done them plenty of time. We all have done it, but we need to understand that they're often going to result in high uncertainty models. So be aware of your risk, be honest. Models are just models. Data preparation and conditioning, it's in my mind the most time-consuming part. Ideally, I want to jump in and just do the fun part and interpret and see my model doesn't match. Why? I don't have a core calibration yet. So it's the most time-consuming part, but it's required for accurate petrophysical prediction. The lithology and mineralogy, they're both inputs in rock physics. And when I say both, I'm saying diagnostic practices and modeling. And last but not least, again, the rock models are a predictive and powerful tool for understanding responses away from the well control. And I would really hope that people who haven't tried them yet go ahead and give it a chance, because they could be powerful predictive ways to understand things away from what we know in the well control. Thank you.